we are going to discuss some important problems in crystal diffraction. First, let us take the problem. Problem number 1. X-ray of wavelength lambda is equal to A is reflected from 111 plane of a simple cubic lattice. If the lattice constant is A, the corresponding Bragg angle in radians is given. There are 4 options are given: pi by 6, pi by 4, pi by 3 and pi by 8. Now this is a simple problem. First you take the Bragg's law. 2d sin theta is equal to lambda. This is for first order reflection n is equal to 1. So 2d sin theta is equal to lambda. Now this is d for a cubical, simple cubical lattice, and the interplanar spacing is given by a divided by square root of h square plus k square plus l square. So which is a divided by square root of 1 square plus 1 square plus 1 square, which is 3, square root of 3. So a by 3. So for one plane. So sin theta is equal to lambda by 2d. You substitute for d, d is equal to a by root 3. So this becomes root 3 by 2. So sin theta is equal to root 3 by 2. So theta is equal to pi by 3. So the option C is correct one. So it's we first consider a very simple case. Now the second problem is a narrow beam of X-rays with wavelength 1.5 angstrom unit is reflected from an ionic crystal with an FCC lattice structure with a density of 3.32 gram per centimeter cube. The molecular weight is given 108 AE atomic mass unit. One atomic mass unit is given 1.66 in 10 power minus 24 grams. So this all the units are in CGS units. Now the lattice constant. There are 4 options are given. You have to find the lattice constant. Now since it is an FCC lattice, the effective number of atoms per cell is 4, because due to the corner atoms there is 1 atom per cell. Each face atom gives half contribution. There are 6 faces, so 6 into 1 by 2, 3. So totally you have the number of electrons, number of atoms per cell is equal to 4. 1 plus 3, which is 4. Now this is M is given atomic mass unit 108. Rho is given. Now the Avogadro number in CGS units is 6.023 in 10 power 23 atoms per mole. Now AQ, this is the volume of the cell, mass by density, and here since the mass is given in atomic mass unit, you have to divide by Avogadro number. So M by Na. Since the mass is given in AMU, actually this is a 208 AMU. So you have to divide by the Avogadro number, so you will get the mass and gram. And the N effective, this is number of atoms per cell is N effective. So this is the required expression, and you substitute the value M, rho, Na, N effective, everything, and you get this is 216 in 10 power minus 24 centimeter cube. So once if you find A is equal to 6 angstrom unit. So your option A is correct. Then for the same problem, the second part, and the sine of the angle corresponding to 111 reflection is. So there are 4 options are given: root 3 by 4, root 3 by 8, 1 by 4, 1 by 8. Now again you have to take the Bragg's law. 2d sin theta is equal to lambda. Sin theta is equal to lambda by 2d. D is equal to, since it is a cubical system, and the interplanar distance is h divided by square root of h square plus k square plus l square, and since hkl values are 1 on 1, so this is a square root of root 3 for 1 on 1 plane. So if you substitute, you will get a sin theta is equal to lambda by 2a root 3, and a lambda values are given. Once if you find the sin theta value is found to be root 3 by 8. So the option B is the correct one. Now take the third problem. Determine the glancing angle on the cube face 110 of a rock salt crystal corresponding to the second order reflection. So this is a second order reflection, that is important. So A is given and lambda is given. So here 2d sin theta is equal to n lambda, here n must be 2. For 1 0 0 plane, d is equal to square root of a divided by square root of 1 square plus 0 square plus 0 square, which is equal to a. So d is equal to a. So if we substitute the value of d, here which is 2, and so d is equal to a. A is given 2.814 Armstrong unit. So if you substitute this value, so this is 2a sin theta is equal to, the order is 2 and lambda is given, and once if you solve this one, sin theta you can calculate, this is 14 degree and 22 minutes. So that can be done. So this is the correct value. Question number 4. The atomic radius of a molybdenum atom is 0.1363 nanometer. Compute the interatomic spacing for 111 set of planes in the molybdenum crystal. The crystal structure is BCC. What is the interplanar spacing for 220 set of planes? Since the molybdenum crystal is a BCC, the lattice parameter is given as A is equal to 4R divided by root 3. So for a BCC crystal, the lattice constant is related to the, so this is the radius of the atom. So 4R divided by root 3, and the radius of the atom is given here. Therefore we substitute here 4 into 0.1732. Once we simplify, the lattice constant is found to be 0.3148 nanometer. The interplanar spacing D11 is given A divided by square root of h square plus k square plus l square. So 1 square plus 1 square. So A divided by root 3. If we simplify, this value is 0.1817 nanometer. Now for a BCC, because this is a molybdenum crystal, which is a BCC crystal which is given. So for a BCC, the allowed reflection, this HKL must be given number. Now this is for 1110 plane, H plus K plus L is equal to 1 plus 1 plus 1, which is equal to, this is R. Since it is an R, this plane does not give a diffraction. That is important. Suppose if we take another plane, 220 plane. For 220 plane, the interplanar spacing D220 can be calculated by A divided by square root of 2 square plus 2 square plus 0 square. Now this value is found to be 0.1116 nanometer. Now here, what is the sum of the HK plus K plus L, which is 2 plus 2 plus 0. This is a even number. Since it is an even number, this plane gives a diffraction. So this plane gives a diffraction line, whereas the D11 plane, it won't give any diffraction. But the interplanar spacing can be calculated by this method. Now let us go to the question number 5. For the given problem, for the problem number 4, calculate the diffraction angle for 220 set of planes for the first order. So n is equal to 1 for the first order. So sin theta is equal to d lambda divided by 2d 220. This is you can get a diffraction only for this plane. So let us calculate this value lambda by 2d. So d, this value of d already calculated, and the lambda used is 0.179 10 power minus 9 nanometer. So once we substitute sin theta is value is found to be here, and theta is 52.37 degree. So the angle of diffraction, this is a glancing angle. The angle of diffraction is 2 theta. So you have to. So you are asked to find the angle of diffraction. So if you want to find the angle of diffraction, it must be you have to calculate 2 theta, because this theta is a glancing angle. Angle of diffraction is 2 theta. Okay. Now, before doing some problems, let us remember the following rules that we are going, because these rules are very much important in calculating the allowed reflections for the crystals like the simple cubic, BCC, FCC, and diamond cubic. Now, if you consider a crystal for a simple cubic, the values h square plus k square plus l square, all values are allowed. So all values of h square plus k square plus l square are allowed for a simple cubic crystal. So the reflections are allowed. So for all values of h square plus k square plus l square for simple cube. Now if you let us take a BCC lattice. For BCC lattice, only when the sum h plus k plus l, if it is possible only for HKL plane, where h plus k plus l must be even. So that is important. The crystal is FCC, then the h, k and l, all the individual numbers h or l and h, k and l, they all are even or all are odd. So for BCC the sum must be even number for allowed reflection. For FCC, if you take the individual values h, k and l, all the h value, k value, l value, all are even number or odd number, then only their reflections are allowed reflections. For a diamond cubic, when h, k, l are odd or even, the sum h plus k plus l should be divisible by 4. So these rules are very much important. You have to remember this rule so that you can do this problem very easily. From extinction rule, we can derive the ratio h square plus k square plus l square value for all the allowed reflections. So for simple cubic, the ratios are h square plus k square plus l square ratios are 1:2:3:4:5:6:8. So you must remember this one. You can remember it easily. For BCC, so 1:2:2, 3:4:5:6 and 7. So there is a difference here. 1, 2, 3, 4, 5, 6. The seventh position. For SC it is the ratio, the number is 8. For BCC it is 7. For FCC it is quite different. The 3:4:8:11:12. So this is for FCC. For a diamond cubic, 3:8:11:8, 16. So this, if you remember this ratio, you can do the calculation very easily. So these are the ratio of h square plus k square plus l square. But the sin square theta values, they are proportional to h square plus k square l square. Therefore, this is the same. Sin square theta 1, it is sin square theta 2, for sin square theta 3 and so on. For simple cubic, it is the same. 1:2:3:4:5:6:8. For BCC, it is sin square theta 1 is to sin square theta 2 into sin square theta 2. So this is a 6:7. So this is different. Here 7, it is 8. And for FCC, the first number begins from 3. 3:4, 8, 11 and 12. And for diamond cubic, the ratios of the angle, square of the sin square values are 3:8, is to 11 is to 16. So you remember this ratio. So you can do the calculation very correctly as well as quicker. You can do it very easily. Now let us take this problem using the above rule. So using the above rule, you can calculate this. You can find out the values very easily. Now let us see. Let's take question number 6. The first reflection from a BCC crystal has a Bragg angle theta is equal to 22.2 degree. The second reflection will be theta of. So you are asked to find theta for the second reflection. So sin square theta 1 is the first reflection. Theta corresponds for second reflection. Theta 3 corresponds to the third reflection. So here they are asked only first reflection, second reflection. So the crystal is a BCC. Since it is a BCC, the ratio sin square theta 1, sin square theta 2, because there are only 2 reflections, to find the ratio. From the table you can see it must be 1:2. So it must be 1:2. So sin square theta 1 is to sin square theta 2 is equal to 1:2. We need not remember we need not worry about the other numbers because only the 2 reflections are the relation between the 2 reflections are needed here. So sin square theta 1 is to sin square theta 2 is equal to 1:2, or sin square theta 1 by sin square theta 2 is 1/2, or sin square theta 2 is equal to 2 sin square theta 1. So taking the square root, sin theta 2 is equal to root 2 sin theta 2 value. So from this the theta 2 can be calculated, which is theta 2 32.3 degree. So theta 2 is equal to 32.3 degree. So the answer A is correct. So this answer A is correct. Here the problem, the first order reflection, the angle is given, and for the second order reflection there are 4 options are given here. So one of the values is 2 times this value. So 22.2 degree here, 44.4. In order to mislead you, the options are, one of the options will be given like that. So you must be very careful because the option 4 is given. Be careful in selecting the answers. The next question is question number 7. The first reflection from a FCC crystal has a Bragg angle, theta is given. The second order reflection, this is sin square theta 1 by sin square theta 2 is equal to 3/4. For BCC it is 1/2, 0.5. FCC it is 0.75. You can remember very easily. 3/4. So from this, sin square theta 2 is equal to 4/3 sin square theta 1. Sin theta is equal to 2/√3 sin theta 1. Your theta is given 21.5 degree. So you give this value. So if you simplify this one, theta is found to be 25. So this is your correct answer. Option B. So the answer is option B. So these problems are often asked in your NET examination or GATE examination. If you refer your previous year question paper, you can see there are problems of this type that are asked. Now then question number 8. Sodium chloride is a crystal which is FCC with a basis consisting of Na plus Cl minus ions separated by half the body diagonal of a unit cube. Which of the planes corresponding to the Miller indices given below will not give rise to Bragg reflection of X-rays? So there are 4 reflections are allowed when HKL are all are odd or all are even. So for FCC this is important. All are even or all are odd. Mixed value numbers HKL, the mixed numbers are absent. Mixed number means some even, some odd. So among the 3, if any one is, one alone is odd, if any one is even, then this is a mixed number and this is not allowed. Now 2 to 0 even number, option A. Option B 2 to 2, 4 to all are even number. Option C 2 to 1. There are 2 even numbers, 1 odd number. So the mixed value, this is not allowed because the question is will not give the given, so it won't give the error. So this is the correct option. Option D, all are odd numbers, so it will give reflections. So all the numbers HKL number must be even or odd. So option C is a mixed number, so it won't give the Bragg reflection. Question number 9. A metal with body center cubic structure, so the first diffraction peak at a Bragg angle of theta is equal to 30 degree. The wavelength used is 2.1 angstrom unit. The volume of the primitive unit cell of the metal. So you are asked to find the volume of the primitive cell. Now let us take the Bragg law. 2d sin theta is equal to lambda, because the first diffraction peak, so n must be 1. So from this find d. D is equal to lambda by 2 sin theta. Theta is given 30 degree because theta is given as 30 degree. So if you substitute, lambda is equal to 2.1 angstrom. So because lambda is also given 2.1. So from this we can find the d. So the interplanar spacing is calculated as d is equal to 2.1 angstrom. Now d is related as a by square root of h square plus k square plus l square. It is given as a body centered cubic. So for BCC, for allowed reflection, h plus k plus l, the sum must be given. That is important. So here one HKL for first diffraction peak, 1 plus 1 plus 0. So this is because the HK plus K plus L must be given. So here 1 plus 1 plus 0, this is the first diffraction peak. So you have to substitute the values of different values. The first minimum given number in this case is 110. So this is the first diffraction peak. Therefore you substitute here and this expression for D, a divided by square root of 1 square plus 1 square 0 square is a divided by root 2. So the lattice constant J is square root of 2 times D, and this value is calculated 2.9694 angstrom. So the D is calculated from here. So from this the A can be calculated. The lattice constant is calculated as this way. Now let us find the volume of the cube. Volume of the cube is A cube, which is 2.9694 angstrom whole cube. This is calculated as this way, 26.1822 angstrom unit whole power cube. The volume of the primitive cell can be calculated as the volume of the normal cell divided by the N effective. N effective is the number of atoms per unit cell in the BCC structure. For BCC structure, N effective is 2 because there are 8 corner atoms. Each corner atom is shared by the neighboring 8 cells. So the contribution of each atom to the particular cell is 1 by 8. Since there are 8 atoms, the contribution to the corner atoms are 8 into 1 by 8, which is equal to 1. Already there is a 1 atom at this center of the cell, body center position. So the total number of atoms per cell is 1 plus 1, 2. So the effective number of atoms per cell is 2 for BCC crystal, that we have discussed earlier. So if substitute the value of N effective is equal to 2 here, the volume of the primitive cell is 26.1822 divided by 2 times A angstrom unit 4 power 3. So once if you simplify this one, this is 13.09 angstrom unit 10 power minus 3. So this option B is the correct answer. So this B is correct. The next problem, the structure factor of a crystal of identical atoms of form factor F is given by the expression. This is SHKL. This is S is structure factor, which is since all are identical form factors, so f can be taken outside from the summation sign. F into sum over j, sum over j, exponential of minus I 2 pi xj h plus yjk plus zk l. Hk l are the Miller indices. Xj, yj, zj are the position of the coordinate of the atom. So they are the coordinate of the atom. Hk l are Miller indices. Which of the following statement is correct for diffraction of peaks for a body-centered cube and face-centered cube? Now here there are 4 options are given. Now this is given as BCC crystal. So this is a BCC crystal. For BCC crystal, the x, j, yj is at the position of the atoms are one is at the corner atom 0 0. The coordinate is 0 0 0. The another one is a body centered atom half half half. Now for FCC, so BCC and FCC. For FCC, there are 4 atoms. The coordinates, the position of the atoms are at the 4 positions. One is at the corner atom, the another one is 0 half half, one other one phase. This is the atom is the second phase. Half half 0 is the position of the 4th atom, which is the position of the atom is the 3rd phase. There are 3 atoms at the center of the phase and 1 at the corner atom. So these 4 atoms are the position of the atoms in the FCC lattice. Now for BCC lattice, now you take the expression, this is the structure factor, the expression for the structure factor. If you put 0 0 0 in that expression, the term will be f into, the first term will be 1, and for the half half position, you substitute xj is equal to half, yj is equal to half, zj is equal to half, and this term reduced to this form for BCC position. Now here, if h plus k plus l, this number is an odd number, and then e power minus I pi into odd number is a minus 1. Already there is a plus 1, minus 1 reduces to 0. So the term is reduced to 0. The structure factor is 0 for HKL is odd, and if it is an even number, this exponential factor, this reduces to plus 1. So this is 1 plus 1, 2 times f. So when h plus k plus l is even, this is 2f, odd it is 0. For BCC, sorry, for FCC lattice, there are 4 corner atoms. First, you substitute for xj, yj, zj is equal to 0 0. Then the term will be, first term is 1, and for the second term, if you substitute 0 half half, you will get this expression. Half 0 half, you will get the third expression. And if you substitute for xj, yj, z is equal to half of 0, you will get this third term. So there are 4 terms corresponding to each position. Now, if all are odd, h, k, l, all are odd, or all are even. So if 2 numbers, all the 3 numbers are odd, now here odd plus odd number gives even number. So therefore the second term will be plus value, third term will be plus value, fourth term will be plus value. So there are 4 terms here. So for all are odd or even, this expression is for if partially odd, partially even. Now here among the 3 terms, 2 terms negative, only is a positive term. Therefore the expression becomes 0. So for the structure factor is 0 if it is a partly odd or partly even. So now let us use the result by choosing each option. Suppose if we choose option A for BCC, if it is for BCC, if h plus k plus l is odd 0, if it is even, it is allowed. So 2 plus 0 plus 0 is even, so it is allowed. 1 plus 1 plus 0 allowed. 2 plus 2 plus 2. So all are even, so it is allowed. For FCC, all the numbers must be even or odd. So 1 is odd, 1, 1, 1. All are odd numbers. So here we are not taking the summation. Each number, HKL number must be odd. So this is allowed. 3, 1, 1 allowed. 400 even number 400 this is all are even number. So this is allowed reflection. So suppose if you take B 210, this is a mixed number for BCC, and 2 plus 1 plus 0. So these are all are so once if you find the summation, this is R, but 110 this is 2. This is so this is even number. This is allowed. 2 plus 2 even number allowed. Whereas 210 this is R number. So this is not allowed. So this is not an allowed. But if you take FCC, this 111, 311. So though this is allowed for BCC, since one HKL value, these values are not allowed. So this is not allowed. So these you won't get a diffraction peak for this one, BCC. So similarly, if you choose C, you can find this one. For BCC, 2 plus 0 plus 0 allowed, all right. 1 plus 0, 2, all right. 2 plus 2, this is all right. Whereas here, this is 111, all right. But 211, there is a mixed number. This is a mixed number, this is not allowed. So this is not allowed. So if you choose all the 4 options, the option A gives the, this satisfies the above condition. A satisfies the 4. So other B, C, D, they are not satisfying. Only A satisfies this condition. So option A is the correct. Now in case of cesium chloride, this is a BCC structure. Cesium chloride is a BCC structure. The reflection for which H prime, K prime, L prime is R, example 100 is not 0, X prime. Now for BCC, suppose if you add these 3, 1 plus 0 is R. If it is 1 plus 0 is R, we expect that it must be 0. But for the cesium chloride, it is not 0. So we have already discussed that if for a BCC structure, if H plus K plus L is R, then there won't be any reflection. But in this case, cesium chloride, though this number H plus K plus L number is R, the reflection here is not 0. Now here that is because the expression for the structure factor can be expressed like this, that we already discussed. S is the structure factor and F is called as the form factor. Now here for BCC, there are the position of atoms are one at the corner point, one at the center of the atom. So if we substitute this value, we have 2 terms. Now since this cesium chloride, cesium is and chloride, they are different atoms. They are identical atoms. Then the F value, this is the form factor, F1 value and F2 value will be equal. But for cesium ion, there are 54 electrons. For chlorine, there are 18 electrons. So the scattering, the scattering power F1 is a form factor, scattering power. This is F1 is naturally, since there are 54 atoms, the scattering power is more when compared with F2. Therefore, the scattering power for cesium chlorine are not equal, they are different. And since the number of atoms, one is 54, another one is 18, the scattering power F1 is larger than F2. So when Hk plus K plus L is R, it gives a minus value. For the first case, if you put 0, 0, 0, this is F1, and here F2 into minus values F1 minus F2. They are identical atoms. F1 and F2 are equal, and so the structure factor is 0. Since the intensity is proportional to the square of the structure factor square, you can say 0. But here F1 is larger than F2, the intensity is not 0. So for F100, though H plus K plus L is a R number, this intensity is not zero. So this is an explanation for the occurrence of the reflection at 100 plane, even though H plus K plus L is odd number. The next question is, now let us find which one is correct. The number of X-ray reflections from KCl is smaller than that of KBr. Potassium chloride is smaller than the potassium bromide powders. So we take a powder photograph and you will find the reflection line for the two specimens. One is for potassium chloride and potassium bromide. And the number of X-ray reflections from KCl is smaller than KBr. And the option B is the number of reflections from KBr. The potassium bromide is smaller than that of the KCl powder. The number of lines both are equal for KCl and KBr. There is no reflection lines from this. So there are 4 options are given. Now, in the KCl potassium chloride, again the number of electrons for K ions and Cl ions are equal. They are equal because for K the number of electrons is 19, chlorine this is 17, almost equal. There is only one electron. Here 19, this is 17. The difference is only 2. So almost equal. So the number of electrons in K plus ion and the Cl minus ions are equal because the atomic number is this is 19, 17. If we take a K plus ion and Cl minus ion, the number of electrons will become equal. The scattering amplitude for K plus and FCl minus are almost equal. So the scattering power, because the scattering power depends upon the number of electrons in the ion, particular ions. So the crystal looks to X-rays as if it were a monoatomic simple cubic lattice of lattice constant A by 2. So though they are different ions, but for the X-rays it is a it seems to be it is a monoatomic simple cubic lattice because they are almost equal number of electrons in the outermost shell. So it looks like a cubic cell, simple cubic cell with a lattice constant A by 2. So only even integers occur in the reflection indices when these are based on a cubic lattice of lattice constant. So this is for a lattice constant A, because it is for this case it is becomes A by 2. So only the reflection integers and they are based on the cubic lattice. So even integers. So if we take a KBr, potassium bromide, the form factor for bromine is quite different from this over here. Because for bromine there are 35, the number of electrons for the bromine is 35, for this here potassium 19, so it is quite different. Therefore the form factor is different. For KCl the form factor for potassium chlorine is same. For the form factor for potassium and bromine are quite different. So all reflections of FCC are present. So for simple cubic, so the first case it looks like a simple cubic with lattice constant A by 2, that is important. Therefore only the even number 220 first number. The next one is 220, 222, 400, 420. So if we divide the number by 2, this is 100, 110, 111, 20. So you will have a number like this for a simple cubic. Among these, you have to select these numbers 200 because since the lattice constant A by 2, then we have to choose only these numbers: 200, 220, 222, 400, 420. All these even numbers you have to pick. You have to choose. For FCC, all the numbers, all the allowed reflections for FCC. The first reflection is 111. All the numbers are even, all are odd. The next number is 200. The next number higher values HKL values 220. The next is 311, 220, and so on. So 1, 2, 3, 4, 5. You can see 5 here. 3, 6, 7, 8. The number of peaks corresponding to FCC is larger when compared with the number of peaks corresponding to simple cubic, because some of the planes are missing for SC simple cubic. Therefore, the number of lines in potassium bromide increases. So among these options, the number of lines in potassium bromide increases. For FCC, the number of these are the there are more reflections you can see for FCC when compared with the simple cubic, because this simple cubic is a cubic of lattice constant MIT. So some of the planes, reflection planes are missing. So only these reflections planes mentioned here are present. So when you compare these two, the total number of lines in KBR is larger when compared with the total number of lines in simple cubic. So number of lines in potassium bromide increases. The next question is, in case of FCC crystal with 2 atoms of A type and 2 atoms of B type, H prime, K prime, L prime reflection has intensity. There are 4 options: maximum when all are odd or even. When maximum all are even, option C is maximum when all are odd. Option D is maximum or minimum, depends on which the atom occupies its specific position. Now here you take the FCC crystal. The atoms are located at 4 positions: 0, 0, 0, first position, 0, half, half. Because of the base center crystal, there are 4 positions, the location of the atoms in the FCC crystal. The structure factor, the expression for the structure factor is also given, and we already discussed. Now you substitute the value of the position of the first coordinate, first atom, 0, 0, 0. So you will get this first term, and if you put a 0, half, half, you will get the second term. If you put xj, yj, z, half, half, 0, you will get the third term. If you substitute half 0, half for xj, yj, zk, you will get the fourth term. Now we assume that there are A1, 2, 2 atoms, 1 and 2 are, the atom A is located at 1 and 2, and atom B is located at 3 and 4. First let us assume. So the type A atom is at position 1, 2. There are 4 positions. Type 1 atom is at 1, 2. Type B atom is at 3 and 4. So for 1 and 2, the atom is A, the scattering power is same. So for 1 and 2, the scattering power, this is here F1, F2, and for 3 and 4, this atom B, so the scattering power is B. So F1 is the scattering power of atom A, and F2 is the scattering power of B. So the expression here, you have to put F2 here and here also F2. Now, when HK are odd and L even, if you choose, then the structure factor becomes. So if you in this above expression, if HK odd and L even, and if you substitute, the first term is F1 and the second term is minus F1 and third term becomes F2, fourth becomes minus F2. So the structure factor is 0 and the intensity is proportional to the structure factor, therefore the intensity is 0. And suppose KL odd and H even, then the structure factor here becomes F1 plus F1 minus F2 minus F2. Then the structure factor is 2 times F1 minus F2, so the intensity is maximum here. Again, if when L is equal to H, is R and K is equal to M with the intensity. So there are the atoms two atoms are atoms A is at location 1 and 2, atoms B at location 3 and 4. For different values of possible values of HKL value, you will find one case it is intensity 0, the other case the intensity is maximum, another case intensity. Now, if we change the location, suppose for A is equal, atom A is at 3 and 4, atom B is at 1 and 2, you notice that the intensity is 0 here in this case, again the intensity is maximum here, that intensity is 0 for the different possible values of LH and K value. Now the important thing is, suppose if we choose, if atom A is at 1 and 3 and if atom B is 12, so the atoms are at different locations. Two atoms are at 1 and 3 and atom B is at 2 and 4, then the structure factor now becomes this. So in the previous case the intensity is 0 when HKL or HK odd and L even, you notice that the intensity is maximum here, whereas in the previous case it is intensity is 0. And here also the intensity is 0 when HK KL values are odd and H is even, and LH or K is even. So from this you notice that when the atom is at location 1 and 2 and 3 and 4, the intensity is maximum when HKL are odd and H is even, whereas when the location is the A is at 1 and 3 and B and at 2 and 4, the intensity is 0. And therefore this suggests that maximum or minimum depends on which type of atom occupies the specific position. So from the above illustration you can easily note that the maximum or minimum depends on the which type of atom occupied the specific position. So the option D is the correct.